Okay, welcome back to Real Analysis. Continuing our work in Chapter 7, sort of surveying the results that we learned about differentiation and the applications of the derivative in calculus. We're going to take a look at section 7.7. Title of it is Monotonicity. In your calculus courses, first semester calculus courses, you probably called the main result of this section something like the increasing-decreasing test. And you used it to classify local extrema of a differentiable function. Okay, so we're going to start off with kind of some terminology. It's basically a terminology review because we applied these same kind of terms to sequences of real numbers. But let's kind of talk them through here. So 4 terms being defined. Every single one of them has the same preamble. So we've got some interval and a function that's defined on it. Okay, so function f on an interval of real numbers. So what are we going to, the terminology that we're going to use? Well, the function is non-decreasing on that interval. If whenever you pick 2 inputs of it with say one less than the other, x1 less than x2, then f of x1 is less than or equal to f of x2. Okay, so non-decreasing in the sense that as the inputs get bigger, the outputs cannot get smaller. They can stay the same, but they don't decrease. Excuse me, non-decreasing. Related but subtly different notion. If we say that f is increasing on I, well, then as the inputs get bigger, the outputs get bigger. Okay, so increasing is a stronger condition that the output at a bigger input has to be strictly bigger. So it's more than saying it can't get smaller; it actually has to get bigger. All right, and then also kind of on the flip side, we might call a function non-increasing or decreasing. Once again, the inputs are always getting bigger. We kind of read these things from left to right on the number line. It's non-increasing if the outputs cannot get bigger. So as the inputs get bigger, the outputs can only get smaller, but they might be equal. It's decreasing if the outputs have to get smaller. All right, so the exact same adjectives that we applied to sequences. We talked about sequences being non-decreasing, increasing, and so on and so on. All right, if we say that a function's monotone, then we mean it's one of these 4 things. So a monotone function is either non-decreasing, increasing, non-increasing, or decreasing. It has to be specified. So monotone is just sort of a catch-all. Let's look at just some real quick examples. I'm going to leave the details to you, but for example, if you take the cubing function on the real line, that's an increasing function. Okay, if you take 2 real numbers, one is bigger than the other, then the cube of the bigger one will be bigger than the cube of the smaller one. Cubing function is an increasing function. The second example is designed just to show you that functions don't have to be continuous or differentiable or anything. If I take this piecewise function, it's given by those 2 linear functions. I'm going to let you draw the graph. That's a decreasing function on the real line. It's not continuous. It's not continuous at 0 and hence not differentiable there. It is continuous and differentiable everywhere else, but it's a decreasing function. Okay, its outputs get smaller as the inputs get bigger. The characteristic function on the rationals, the function that's 1 on Q and 0 on the irrationals, it's not monotone. It's not increasing, decreasing, non-increasing, non-decreasing. It keeps taking on the value 0 and 1 in every single neighborhood. So in any interval, I can choose an x less than an x1 less than x2 and have the values be bigger than each other, smaller than each other. So it's not a monotone function at all. Okay, and there's lots of examples. The sine function that we've been using a lot in the differentiation chapter, it's not a monotone function. It increases sometimes, it decreases sometimes. Okay, so the following theorem, the main theorem of this section, and the mean value theorem is going to make quick work of its proof. It comes up a lot in calculus. It's usually called the increasing-decreasing test in calculus books. Okay, so what's the preamble? Functions defined on an interval I. So we've got a function f defined on an interval I, and we're assuming it's differentiable on that interval. Okay, so this function has a derivative at every single point in this interval I. And there's 5 parts to the theorem, actually. I won't kind of narrate, well, maybe I will, each one of them. But so in each one of them, it's some hypothesis about the derivative. So in the first one, if the derivative is non-negative for every value of x in the interval, then the function is non-decreasing on that interval. So this is an example of how the derivative gives information about the function. Derivative non-negative, function's non-decreasing. If the derivative is strictly positive, then the function is strictly increasing, or just increasing in our terminology. 3 and 4 are just the flip side. If the function is less than or equal to 0, the derivative, that is, on the interval, function's non-increasing. If the derivative is strictly less than 0 on the interval, the function is decreasing, or strictly decreasing if you want to emphasize it. And then 5, we've already proved, actually, if the function's derivative is identically 0 on the interval, then the function has to be a constant. We gave a direct proof of that from the mean value theorem last time. It actually follows from the earlier parts too, because if the function's derivative is identically 0, well, then in particular, it's greater than or equal to 0. So the function is non-decreasing. So its values can't get smaller, but it's also non-increasing. Its values can't get bigger. Well, the only function whose values across an interval can neither get bigger nor get smaller is a constant function. So 5 actually follows from 1 and 3, or you can take a look at the mean value theorem proof we gave last time. In some sense, that's a mean value theorem proof too, because 1 and 3 follow from the mean value theorem. Okay, so just to kind of set the stage here, given the notation above, I is an interval, f is differentiable on it. Let's pick a couple of points in I and say that x1 is less than x2. And just to kind of hit the hypotheses, f is continuous, or sorry, f is differentiable on I, so it's continuous on I. So then in particular, it would be continuous on the closed interval between x1 and x2. And in particular, it would be differentiable on the open interval, the interior of that interval. Okay, so the hypothesis of the mean value theorem are satisfied. The mean value theorem says that there's a C that satisfies that equation. In the mean value theorem, it's usually written as a fraction, but I've just multiplied both sides by x2 minus x1, right? So that's just the equivalent version of what the conclusion of the mean value theorem. There's some C so that the derivative at C is equal to the change in the outputs over the change in the inputs of the function. Okay, so now let's just look at some hypotheses here. Like in part 1, we're assuming that f prime was greater than or equal to 0 for all x in the interval. So in particular, for all c in the interval, f prime would be greater than or equal to 0. Well, then looking at the right-hand side of this equation, I'm taking a non-negative number and multiplying it by a positive number. So the result on the other side is non-negative. So that tells me that f of x2 minus f of x1 is greater than or equal to 0. That's precisely what it means for f to be non-decreasing. F of x2 has to be at least f of x1. Okay, if f prime is strictly greater than 0, okay, well then this number, f prime of c, is positive. x2 minus x1 is positive. The product of two positive numbers is positive. So in that case, I can say that f of x2 minus f of x1 is strictly greater than 0. That is, f is increasing on the interval. Cool. 3 and 4 are treated similarly. I'm going to leave the details to you, but you just have to kind of think about the signs. And like I said last time, that 5 was shown last time. So that completes the proof of our theorem, the increasing-decreasing test. This will be a short video again today, but let's just end with kind of a remark. You should be a little careful because some of those statements above the converse fails, but it tends to be kind of a misused thing, especially by students in calculus. So be careful. So just for example, the converse of part 2 fails because that cubing function example that we looked at above, it's an increasing function on the real line. So in particular, say on the interval from -1 to 1, but its derivative is not positive on that interval. Its derivative takes on the value 0 at 0. Okay, so it's not true that if you have an increasing function, its derivative will always be strictly greater than 0. Its derivative might equal 0, like for the cubing function. I'm going to leave it kind of as an open-ended question. What about the converse of 1? Yeah. So what do I mean by that? If you take a non-decreasing function that's differentiable, is it true that its derivative is always greater than or equal to 0? I'm going to leave that as an open question. But certainly, this example shows the converse of 2 fails. The converse of 4 would fail. You could take the negative of the cubing function, for example. And then my last remark is that the hypothesis above, we were assuming the differentiability of f on an interval, and everywhere the hypotheses about the sign plus or minus of the derivative was an assumption about on an interval. Because it's tempting, at least maybe I guess I'm admitting I get tempted. It's tempted to think that if you have some function it's differentiable and its derivative is, say, positive at a point, then it's tempting to think like, well, okay, that function should be increasing in some neighborhood of that point. Yeah, so I'm dropping the assumption that the derivative is positive on an interval, but I'm just saying, suppose the derivative is positive at c for some c, just one point. Well, in general, it's false. That you can take a differentiable function, its derivative is positive at some point, and there is no neighborhood around that point on which the function is increasing. So I'm not going to include the example in this lecture, but if you're interested in it, you can pursue these ideas further. The author kind of lays out a breadcrumb trail on how to construct such an example. It won't even look like an unfamiliar function. It's something that we've talked about before in this course. It's sort of a nice family, if you like, of functions for such counterexamples, but you can check that out. It's exercise 7.74. Okay, thanks for listening.